Alright, Oliver, let's see your twist.
I apologize for this, but the thought kept going through my head as I looked at this picture. This is Zenith 1 or something. So today, the main philosophy is that Alexander polynomials and twisted Alexander polynomials are group invariants. They depend really on the isomorphism of the group and group data. This is not really a surprise to group theorists who have known about the classical Alexander polynomial for years. If you go back and you look at Magnus Carus and Solitar's book on combinatorial group theory, you'll find something there called the L polynomial. And it's one of the names it was given, when it was realized that you could compute these things generally. Just very briefly, let me suggest a category that's kind of interesting, because I'll come back to it at the end of today's talk and show you what happens in the twisted case. So what's pi? It's a finitely presented group. And what's epsilon? Well, as before, it's a homomorphism from the group pi onto z, which you can think of as generated by t. And there's a category here. You can think of these as objects, and a morphism from one to the other is a homomorphism.
Epsilon 1.
Oh, what do I have?
Epsilon 1.
Oh, epsilon 1, thank you. This would be, means that phi is a homomorphism that makes this diagonal commute. If you've got one of these objects, you can look at K, we'll call this the kernel of epsilon, which for a knot group is pi prime, the commutator subgroup, but generally is not, it's just a normal subgroup. And then you can look at K, abelianized, and that's a module. It's a finitely generated module over ZTT inverse. And so you can define delta to be the what's called the order of this module. It could be 0. So the order, let's call this h. The order of h. And let me not go into what the general definition of order is, but for a knot group, it's exactly what we've been computing.
If h is tangent, then that would not be.
Exactly. Yeah. In fact, it's the vanishing of delta that tells you that you have non-torsion. That's not, you don't have a torsion module if delta is non-zero. And so let's notice I've suppressed epsilon in the notation here. But when I write this, epsilon's always lingering there. Now for a knot group, there's really only one choice of the sign of epsilon. So it's not such a big deal and you don't notice it. But what's one interesting corollary of all this is that if you have this situation where you have an onto map, then in fact you can show that, well, then if you look at phi restricted to K1, now I'm using the subscripts in the obvious way here, so don't think this is a second homotopy group or something. So the phi of K1 restricted to K1, excuse me, would go from the kernel of epsilon 1 to the kernel of epsilon 2, and in fact this would be onto. It's very easy to see that from the commutativity of the diagram. And so, and in fact then we induce a map from H1 on page 2.
Why is it clear that K is finitely generated?
Why is it clear that K is finitely generated? Because this is an invariant. Oh, K. I'm not saying K. No, I didn't mean K. No. But we're abelianizing. This is not finitely generated, generally. This could be a commutator subgroup with a
All
finite two.
right.
Yeah, but when you abelianize it, then you're over an invariant ring, and it works. So, okay, so now you have an onto map, and now just the ordinary theory of order ideals tells you that in fact delta of pi 2 divides delta of pi 1. So, for example, you immediately get a way of testing whether or not there's an epimorphism for one group or another group that preserves these augmentation homomorphisms. And you can ask this question about, given two knot groups, is there an epimorphism? Twisted homology has been used to give obstructions that are finer than this one, and I'm going to come back to that, I hope today. I'm going to try that's the way to get there. So what about the multivariable polynomial? And so similar statements hold for the multivariable if you properly define it. And I haven't really done that for general groups. And also for twisted invariance. And that's also going to be true, properly done. There's a category lurking there as well. So today the reference is Wada's paper, Twisted Alexander Polynomial. If you are doing a search, it is polynomial, not polynomials, for finally presented groups. And this is a paper that appeared in Topology, volume 33, 1994. And a lot of the details that I'm going to sensibly skip today are found there. They're not. Whatever I skip today, I guarantee you is elementary and not very long. So let me set up some notation that we use for the day. I'm trying to keep the notation, and Susan and I are both trying to keep the notation consistent. So pi now is just a group that has a presentation x0, x1 of xn, and relations. Now I'm going to change the n to m. And I'm also going to change the equal bracket number. So this is not necessarily equal to n. But by adding extra relations, if necessary, we can always assume that that n is at least as large as n. Let's always do that. And let's assume that epsilon is a homomorphism to z to the d. And this is, I'll think about this is generated freely by t1 through td. So. Oh, yeah. Okay. Let's make a comment. Thank you.
Is this a subjection?
Yes, thank you. Yep. And so lambda, as before, will be a ring of Laurent polynomials where R is an invariant U of D. And gamma will be a representation, linear representation of G of MR. We're going to continue to use the notation that little xi goes to capital Xi. If my handwriting confuses you, the context should make it clear. Usually so. Now, this induces a map on the group ring But if you go to the group ring, you know, you add two elements of invertible matrices, you don't necessarily get an invertible matrix. So here you're just going, of course, to n by n matrices if you want to pass it to the group ring. And we do. And now we've combined the two representations. If you multiply them, I prefer the music. If you multiply them, the usual notation for this, which has caused objections to lots of algebraists that I know, but nevertheless, this is the notation for, that's a tensor, z pi. Now we're going to go to n by n matrices of the group ring. All this is the homomorphism that sends mu xi to the augmentation, which is some monomial in the t's. This is a monomial in the t's times the matrix xi. That's all. So imagine the representation that you get that way. And now you know you've got a free group. I'm going to use F today for the free group on x0 up to xn. And you know you've got a projection from the free group pi. Just plot out by the relations. So we're going to precompose. We're going to go from precompose with F to pi to get this thing which should come up a lot, capital Phi, following Watta's notation as much as possible. This is going from the group ring of the free group to the matrices, n by n matrices over lambda. So
is this related in special cases to the Rayleigh polynomial that we're using a symbol for? Or?
The Rayleigh polynomial, nothing here yet is
No,
giving it.
yeah.
Oh, I know what you're asking. No, it's not. And you know, it's a local variable.
Just asking.
Yeah, it's a good question. You run out of letters, don't you? So that's why colors. So
like Chinese characters.
what's that?
Like Chinese characters.
So now I want to put together a matrix, and those who know the term, this is a Jacobian matrix. And I want to, here I've got to depart a little bit from Watta's notation. I want to use script M because we've already used Roman now. This is a M by n plus 1 matrix. The rows are going to correspond to relations as before, as we did it with the calculations of the Alexander polynomial. And the columns are going to correspond to generators. That's why we have the M and the N in that order. With ijth entry. What's the entry? All right, we're going to take the Fox partial derivative of the ith derivative with respect to the jth variable. That is a word in the free group. It's in the group ring. And then we're going to, really all we're going to do is evaluate the xi's at the correct matrices weighted by the correct monomials. That's really all this is saying. I'll show you an example in a moment. The notation is necessary just so we can communicate with it, which we're doing. It's pretty easy. So, so this has got to be evaluated here. And this is in, of course. Let me say just a brief word for those who haven't seen the Fox calculus. Just the minimum amount that you need to do this calculation. Neil said something about it already, but I'm not sure if everybody was at that session. So what we have are homomorphisms from the free group to the group ring. And we just need it going from F to here. You can extend it over the group ring to the group ring, but we don't need to do that. And we'll keep the formulas just a little bit simpler. Huh?
It's not a homomorphism.
Oh, I'm sorry, it's not a homomorphism, it's a derivation. Sorry, yes. Of course. That's the point.
Right.
So, all right, so,
I just wanted to make sure.
yes, thank you very much. Leave me alone. We won't use that. Okay, so the evaluation on a generator is the Conjugacy. And that's rule number one. And rule number two is that you've got a product rule on words. And this is, it's getting nearer. The u dx, j plus u dv dx j. Just like,
You left them supposed to.
No, he's okay. 'Cause
no, good. Good, yeah. So actually, these are all you need. This is it. So, you know, as a consequence, corollary of the definition, as an obvious consequence, first of all, you get that the Fox partial 1 is 0, and that's just because 1 times 1 is 1. And if you apply this or something, you get that right away. Yeah, you get it here for number 2. And also, you get, as a consequence, and this one's good to state, xi inverse, xj inverse, is, I don't mean to suggest there's a minus sign here. This is a minus xj inverse. All this is motivated by path lifting to the universal cover of the bouquet of circles representing the free group. And play around with that if you haven't seen it before. You'll see immediately, I think, why this is path lifting. So that's all we need here for this. And so I'll show you by example, too, what this is. So now we've got this big matrix. You see, we'd like to take a determinant, but this is far from square. And it's not even a matrix of elements of lambda yet. We've got matrices of matrices is what we've got here. So the first thing we want to do is delete a column. Now, right now, this is a matrix of matrices. And we're going to delete a column. So for any j equals 0, 1 up to n, let script mj be mj, and with the jth column deleted.
A column of matrices.
Yes, this is a matrix of matrices right now. That's right. So we, for example, strike out the first column. And now, regard mj as an mn by mn matrix over n. Okay, so we're almost to the point we can now take determinants. The only catch now is that, of course, we have to take square submatrices. So we have to pick rows from this big matrix. We have to pick rows in which we delete enough of them will get a square matrix. Let me just say a word. There's an early paper on the subject by Boji, Zhang, and Wang that's often referenced. And they just say a word. In that paper, there is a mistake in the definition. They forgot to remove the parentheses before they tell you to get the square matrix. You can't just take minors corresponding to blocks. You have to remove the inner parentheses and then look at all the possible square matrices. It won't work otherwise.
Because we've ensured that m is bigger than little m is bigger than little n, then we just have to delete rows.
Well, I mean, look at this situation right here.
Yeah.
I mean, if I have this remaining,
So you just
it's not enough to just take that block or that block or that block.
Right, you're not deleting rows of matrices, but you are deleting rows in the original
That's right.
thing. You
That's all I'm saying. Yeah, the order of deletion here is very crucial. It didn't affect anything in the paper, as far as I know. It was just kind of a slip in the definition, and then you could be computing this and getting the wrong thing very fast. Okay, so, all right, so now,
I have another question.
yeah.
Here we're holding on to J. Is that, I mean, generally, you know, we've just thrown something out, so is there a particular reason that we're...
Think about the fact that we were deleting the 0th column in the things we were doing. J was 0. And for vertical presentations of links and knots, you'll just be able to take J equal to 0. If you've got a more delicate presentation where these generators are not all Vertinger generators, and they can go to different things on their epsilon, then we really do have to worry about which column we delete. And that's the point. You can delete something that messes you up, and the denominator that you're trying to divide by in the definition of the Watt invariant will become 0. So that's the reason. We do want this generality because we don't want to have to just restrict ourselves to Vertinger presentations. It's too much work. All right, so so let me make a comment that if x0, x1, xn, r1 through rm is a Vertinger presentation, then m0 is just m as we previously defined it. And convince you of that, here's the trefoil. And we wrote the relations as relations, not as relators. We dropped one. And that's fine, because this is a perfectly good presentation to work with all Vertinger generators. But if you really want to work with these, you should write this way. And likewise here, because this is going to be a word in the free group. And then m0 will be, well, the column that will correspond to taking the Fox partial derivative of this with respect, this should be a 1 and a 2. Fox partial derivative of this with respect to 1, x1. See, with respect to x1, there's only one partial derivative that's non-zero. And that's obtained here. You just, all you take is x0. And then you evaluate it at phi. And the Fox partial with respect to, I said with respect to x1. With respect to x2, it's going to be minus this whole thing. But you see, in the knot group, this is a relator. This represents 1 in the knot group. And when you evaluate phi on 1, of course, you get 1. So you see right away, this is just minus 1 minus the identity matrix here. And over here, well, this is just t times the matrix x0 for the knot group, because the augmentation epsilon of a Vertinger generator is just t. And it's t times the matrix that gamma assigns to it. So this is exactly what we wrote down before, and the other two are similar. So I'm just trying to show you that for Vertinger presentations, this is mimicking everything we've been doing. Questions? So now it's we just take some rows and make this square. Take a determinant. We're almost there. So that I'm going to use script I. What I use is Roman I. We've already used Roman capital I for matrix, so let's not make life really unpleasant with script I. The n tuple of indices in 1 up to mn. And let mji be the nn by nn matrix consisting of those rows. of MK. Sorry about the formulas, but it's good because I need to state something here, and this is the only notation that I can really use to state it properly. First thing we get is this very powerful lemma, which is not a real surprise if you work with Fox calculus much. And the lemma says that the determinant of this square matrix times the determinant of 1 minus xk is equal up to a unit to the determinant of mk, that same choice of I, determinant of 1 minus xj. This is for all capital I choices at j and k. So it's telling us that different choices of j, fixing the choices of rho, different choices of j will be the same up to these characteristic polynomials, essentially, of the
The J is a column.
yeah. The j is a column. Yeah, I'm sorry. Yeah, that deleting the jth row, the kth row will give us the same determinant for the same choice of rows I up to this factor. And in fact, the sign is plus if n is even. N is the size of the matrix. The proof of this is elementary. The proof uses what's called the fundamental Fox formula. And it's a general fact that if you take any word in the free group and you take 1 minus the word, then this can be expressed as the Fox partial with respect to xj of that word times 1 minus xj. And this is true for all w in our free group. So this is just a general fact about free groups and Fox partial rhythms. And this is what makes this work. And it's really just a matter of solving for something and doing a row substitution. And let me not do that. Yes?
You get different cases when J and K are in I or not in I. I mean, is there other information that
I'm not sure
you would get?
what you mean.
You're deleting columns.
Remember that, yeah, remember that
J
J and K are columns.
when you're doing
Well,
I.
I understand,
You know,
I understand that, but frequently we would choose to delete, the same row and column sometimes. Like, I mean, I know you don't have to, but so if there was a thing, I know that there, indices on rows versus columns.
The order of the relators is pretty arbitrary. You just,
That's true.
Remember-
rows are corresponding.
Remember in the problem session when we were arguing over this, whether we delete the same row or the same column, and we decided that it can't be that exactly for the reason that she just said.
we talk later. Yeah, it's so now all you need to do to get an invariant is let Qj be the GCD of all get Mj I as you vary I. Obviously J is fixed here. All the different possible square matrices you get, your major choice J of which column of blocks to delete. You've removed the inner parentheses, then you're looking at all the possible square determinants that you can get and taking the GCD. And that's what Qj is. In the case of a knot, once we've remade the choice of J, there's no choice of I. There's nothing to do. We have a square matrix. So we're there already. But if you've got more relators, then you've got to just do some more fitting. And then the definition is that W is Qj. In fact, I guess at this point it's kind of, well, it's clear that this is the same as the thing we got before. But now this is more generally defined. And the claim, of course, is that this is provided the determinant is non-zero. It could happen, by the way, and so we have to be a little careful. And the claim is that this is an invariant of the group. It's independent of the presentation. So this is what this means there. Sounds like you've already gone over the paper. Did everybody read the paper?
Yeah, Oliver mailed it to all of us.
What?
Oliver mailed it to all of us.
Oh, I was wondering if you all went through it already. Okay, so W gamma is independent of presentation. And the way you prove this is by knowing the fact that any two presentations for the same group are related by a finite sequence of elementary moves, in this case called Tietze transformations, that are very similar to Reidemeister moves. In fact, if you restrict yourself to Reidemeister moves, they correspond to very special combinations of Tietze transformations. And it's by restricting yourself to knot diagrams and vertigo presentations and the Tietze combinations that arise from the Reidemeister moves that you get slightly stronger refined invariants. That's not what I want to talk about now. And as a corollary, if you've got a the situation that we had before in the untwisted case, and a isomorphism here, this follows immediately from this. If you've got this, then now what's the statement? You haven't seen a representation yet. So here comes the representation. For all representations gamma of the second group, if you look at the Wada invariant of the second group with that representation, it's equal to unit to the Wada invariant of the first group. But what you do is you pull back the representation. So here I go forward. For every representation here, I can pull it back. And I'm guaranteed that with these augmentations and this isomorphism, then in fact that these invariants would be the same up here.
So if you don't have an isomorphism, but you have a surjection, then you can
Come
still
to that
hold
right
it back.
now.
Okay.
But that actually requires some proof. And this was a later paper. So that's right. So in fact, there's a theorem of Katono, Suzuki, and Wada, 2005, that says that if B is an epimorphism, then one of these will divide the other in the sense that well, these don't have to be polynomials, because remember that a priori the Wada invariant could be a rational expression, but this thing is guaranteed to be a Laurent polynomial. So so this can be used to rule out the possibilities of an epimorphism, provided you look at the whole basket of invariants you get. You'd say you look at some representation to a fixed finite group. You look at all of them up to conjugacy. You only have to worry about them up to conjugation. You look at what you can get, and then you have to ask whether or not you can. Well, you have to look at all the others that you get into that group, and then you have to check divisibility. And if they aren't all divisible in some way by one thing by things in the other basket, then you couldn't have had an epimorphism.
So for everything in one basket, you have to find something in the other basket.
Right. It helps if there's only one conjugacy clause, but and they've actually been using this to address this question.
So if you're dealing with links instead of knots, do you still get?
Yeah.
Are there non-isomorphic and are non-equivalent knots with the same fundamental group?
Are there non-equivalent knots?
Links. Is that true?
Links with the same. Yes.
Okay.
Yeah.
So does this have any shot of distinguishing those?
Careful with that. Yeah, there are. Yeah.
Okay.
There are links with the same exterior. Does it have a shot? I don't know. But there is something else I should say. If the representation is trivial, here, then the Y invariant is still well defined. This would, in the case of a link, this would just be the usual multivariable Alexander polynomial, at least one way of defining a multivariable Alexander polynomial. And so that thing I started with at the beginning about a category would apply to the multivariable case if you used this definition of an invariant. And here's the proof. Okay. And you get the same consequence. All right. So Susan will probably say a little bit more about this issue of epimorphisms. Are you? John Simon's problem, which is still open in the general case of given a knot group. How many knot groups can you find that are quotients? And the conjecture is only finitely many. And this has been a difficult problem, partly because, well, to a great degree, because you don't really have any control over where the meridian of this knot group is going. If you could somehow ensure that whenever you had an epimorphism, a meridian would be sent to a meridian, life would be a lot easier. And there are many questions here. It would be nice to be able to say more about it. Let me move on because I want to make sure I get to this great example of Lin. And now with this more general way of computing the Y invariant, we can do many more things. And by the way, this is also the key. This point of view is also the key to understanding why there's a fibering obstruction that Friedel and Vidusi, for example, have exploited. Why there's a fibering obstruction from twisted invariants. And we'll be talking about that next week. So, Lin's example. This comes from his paper that motivated all this. And what I've tried to do is translate everything into this language. It looks very different in his paper because he's looking at Seifert surfaces and push-offs, very special types of Seifert surfaces. And he's looking at push-offs and so forth. But this is essentially his example. I mean, it is. So the Treadwell group, again. Pi, you've already written it down. It has three generators. If you use one of the relations to get rid of x2, you get a presentation that's very familiar to people.
Look at the generators.
Was that? Oh, yeah. Right, indeed. This one, 0, 1. Thank you. Okay, so let's write x for x0. Is it okay now? X for x0. And let's write x1 as a times x0. So in other words, let's replace x0 by x. And let's replace x1 by ax0, when a is now going to be in the commutator subgroup. You can do this more formally, Tietze equivalences and so forth, moves on presentations, but it's a simple substitution. And if you do that, you get a new presentation. I've just done this to get rid of that subscript because it's annoying. And now what you get is two generators, x and a, and the relation is ax squared a is x a. So something is called, it's similar to something called a pre-Euclidean presentation. Yeah. A meridian and something in the commutator subgroup. And of course, this could be written as a relator. Okay. And we consider a rep gamma from pi to SU2. And up the conjugation, we can assume that x, this is the image of x, has this form. W bar complex numbers. W is a complex number and its modulus is 1. And a general element of SU2 has the form complex number, and then these are determined minus B conjugate, A conjugate, and we have the condition that A bar plus BB bar is 1. This expresses the situation where you can think about SU2 as the free sphere, and the traces of the elements correspond to the latitudes. And up here at latitude 2, the identity is lonely. Up at -2, down -2, it's here. And the conjugacy classes in SU2 are given by trace. So all the elements of the same trace are actually conjugate, and vice versa. It's a very pretty picture. And yeah, the trace zero matrices. So, if first of all, let me say if beta is 0. If beta is 0, then this is going to be a reducible representation. And if beta is non-zero, then alpha and beta are uniquely determined. By omega. It's not too difficult to check. Now, we only have one relation. And so the Watt invariant is simply the determinant of the partial derivative of that relation, which is called R, with respect to A, evaluated by phi. That's the numerator. There's not much to do. It was a 1-by-1 matrix before we took off the parentheses, and then it became square. And then we divided by the determinant of I minus t times x. And this is not a big surprise down here. I mean, this is easy. This is just t squared minus the trace of x of t plus 1. But it's the numerator that takes a little bit of thought. And the determinant of this is the determinant of, let me just go over here and take the partial derivative with respect to A. You get 1, you get ax squared, you get, so ax squared from that one. From this one, you get minus this. But look, this element is equal to x in the group. So minus this element, the third term of the partial Fox derivative, is just a minus x. So what you can write is identity plus, don't forget the augmentation, ax squared, not a squared x. Ax squared has augmentation 0 plus 2. So that's why you see t squared. And then minus x, and x has augmentation 1, so that's why you see a t. Now, if you expand this, and this is where it's handy to, well, you could do this. You could do this with a very large envelope, or you could use Mathematica. You get t to the 4 minus the trace of x n t cubed. You have to check that, but trust me. 1 plus the trace of x squared a t squared minus the trace of x t plus 1.
So this is the spot in his paper where basically he writes what you write.
Yes.
Okay.
And
it leaves it up to you.
Believe me, if you check it and you let Mathematica simplify it, and then you look at what this is, and you just compute the trace of this matrix, you'll see that it's quite right. I don't think there's an easy way to see it.
Okay.
Yeah. But yes, I checked this very diligently. I had to because I was changing all the terms. He was using different generators, and he was using more of them.
Right.
He had a 2x2 matrix, I have a 1x1 matrix.
Right.
And so it was necessary to really, yeah. Okay, so what about these? Well, XA is the same as X times AX, X inverse, you see? So that's conjugate to XA is conjugate to AX. And AX is just the meridian. AX is just X1. X1 is conjugate to X0 because it's a knot group. These are meridians. So see this. So this thing is conjugate to X1, which is conjugate to X0. So the trace of XA is the trace of X. It's the first thing we can do to simplify this. See that? So what about? This is where you got to do a little bit of. What about X squared? This is really very pleasant exercise in trace identities. You use the fact that the trace of a product is the product of the traces minus the trace of the first times the inverse of the second in SQ2. And also that the trace of the inverse of a matrix is the same as the trace of the matrix in SQ2 because of the form of matrices. Because the eigenvalues come in inverse pairs. And so, pardon?
Can you say is the inverse on?
Yes, thank you. Always. So what about X squared A? Well, the trace of X squared A is the trace of X, the trace of XA. I'm decomposing it as X times XA. Then it's minus the trace of XA inverse, because I get XA. So X times
X.
yes, thank you very much. Thanks. And so this is, and this we've already commented is the trace of X. So this is the trace squared of X. And this is going to be just, this is just going to be X A inverse X inverse, which is the same trace as A inverse, which has the same trace as A. So this is just the trace of A. Okay, that's fine. That tells us how to write this in terms of these two things, which is good. And now the relation. The relation. AX squared A equals XAX. If we group it like this, and we apply the trace relation and then do the substitution, so all we do now is we apply this, and we put this in. Maybe I should skip to the punch or do a line. I think I should skip to the final thing. When we get done, we can factor this out. Really just skip one step, but all I did was apply the trace this to this, and then wherever I had the X squared A, I used this. This is not perfect, but this is equal to that. Did a substitution.
What is the last term on the left-hand side of the equation?
Oh, that's a 2. Oh, and yeah, I should probably make sure it's clear that came about because you had a trace of X squared. And the trace of X squared is trace of X minus trace of the identity. The identity is trace 2. That's where the 2 came from. Thanks for asking that. All right, so now what Lin does is he lets trace A be a variable. Let's call it U, and that's why I'm writing it. I haven't written down it yet, but write it this way. And then when you plug it in, you get U squared plus U minus trace squared X minus 1 plus 2 trace squared X minus 2 equals 0. And this factors remarkably well. It factors, and if U is 2, remember what U is. U is the trace of A. And remember the picture. The only thing that has trace 2 is the identity. Up there at the lonely North Pole. So if U is 2, then A is the identity. Then we get a reducible representation. Because if A is the identity, remember how A came about. That means x0 is equal to x1. x0 is equal to x1. And if x0 is equal to x1, heck, you can send all the meridians to the same matrix. Pick your favorite matrix and send them all there. You've got an abelian representation, and that's perfectly good. The only possibility for irreducible representations come from the second term. So if U is equal to trace X yeah, so the other right. So the other thing is right. If trace A equals trace squared X minus 1, then there's a possibility of irreducibility. Gamma might be reducible. Let me just say, and I'll show you where they are and where the irreducible ones are. But if gamma is reducible, remember the one-dimensional example I did of the Watt invariant, where we send the meridian of the trefoil to just a complex number as a 1-by-1 matrix, and all we got was the classical Alexander polynomial evaluated at that number times t, divided by a factor. And so in this case, what you get is the product of two things of that sort. The two roots, right? One for each of them, and divided by squared. If gamma is irreducible, I'm almost done. And then abelian, these actually arise. Then this implies that the trace of X has got to be 0. And the way to see that is to realize that A and all of its conjugates of powers of X have got to commute, because they're all images of things in the commutator subgroup. And that means that A should be a diagonal matrix. And if you ask yourself what happens if A is a diagonal matrix, you throw it into the trefoil relation, which this is what comes out. Lin doesn't say much about this condition, but that's what you have to do. And in this case, up to conjugacy, X then can be thought of as the matrix 0, minus 1, 1, 0. Susan described this. So this is one of these Abelian things that come out of the work that Friedel and Produci, Bowden and Produci classified. Bowden. How many possibilities are there? So let's see. And so if you figure out what omega has to be, it turns out that omega cube has got to be 1. So that's the. It's interesting. This is not the dihedral group. This is twice the size of the dihedral group. This element has order 4. It's not a flip. So I think this is sometimes called the binary diagonal group. I'm fairly certain that this is the binary diagonal group.
Yeah, it's inverse image
Yeah,
in the
yeah.
S3.
In this case, by the way, we get which factors on the top, and this is just t squared plus 1. This, Susan, I think will say something about this coming up from the irreducible Mendelian representation. And from Mendelian representations, generally you're going to talk about this conjecture about t to the m plus 1 and t to the m minus 1. Maybe. This comes up quite often. You notice the dependency on omega vanishes totally. But if gamma is irreducible, generally, then the trace of A is the trace squared of x minus 1. And the trace of x lies between minus 2 and 2. So solving, this means that, well, trace of A lies between minus 2 and 2. So does the trace of x. But the trace of A lies between minus 2 and 2, which means that the trace of x is less than root 3 in absolute value. Remember that conjugacy classes for the irreducible ones are going to be parameterized by they're going to be parameterized by the trace of x, and hence parameterized by this number, omega. And so you get a situation like this. Where between root 3 and minus root 3, at any level in here, there'll be a any parameter value between here and here, you'll be able to find an irreducible representation. And there'll be reducible ones. There'll be reducible ones if A is the identity. We already talked about those. And I think this is the reason why Lynn wrote this drew this somewhat cryptic picture, which I've been bothered by, labeling this the trace of x, which of course is a real number. But so I think it's sort of like I think he meant like a bifurcation. I'm not really sure. But these up here are the reducible ones, the red ones. And they go from 3 to, oops, they go from 2 to 2, minus 2, and root 3 to minus root 3. And this is the reducible, and the black is the irreducible. And what do the polynomials look like? Well, we've already written down the determinant. It's just a matter of plugging in. We've already written down the determinant of the numerator of W, so it's just a matter of plugging in. Looks like this. T to the 4 minus trace x, t cubed plus trace squared x minus 1 t squared minus trace x t plus 1 divided by, we talked about that denominator, t squared minus trace of x, t plus 1. And so you can see what happens to the polynomial as this parameter, trace x, goes up to root 3 or down to minus root 3. When it hits those values, you suddenly have a reducible representation that we wrote down a moment ago. But in between, you've got these values, and this is how the twisted polynomial would vary according to it. Now, and just one last comment. Lynn was only talking about the numerator if you're reading this paper, which Susan and I have been calling capital D gamma, suggesting it should be within the twisted polynomial, because it's also the numerator. So I'll stop here. Thank you.
Thanks. Any questions? Thanks again.